want to do today is to talk a little bit about these oxidation and reduction reactions following from where we were last time. And then we'll go ahead all the way into the material in Chapter 19, and I'll outline what we're going to do when we get to that. Where we were last time is we finished talking about these reduction and oxidation reactions. And so we've been dealing with oxidation quite a bit with PCC and chromic acid and that. And this was the conversion of, say, an alcohol up here in the upper right, make it bigger here, to carbonyl-containing compound, an aldehyde or a ketone, for example. And we can go in the reverse direction, where if we wanted to change a carbonyl-containing compound to an alcohol, this is formally a reduction reaction. And then we ended introducing two reagents that are common reducing agents. This first one is sodium borohydride, NaBH4. And then number two is lithium aluminum hydride, LiAlH4. We made this assertion that one is weak and one is strong. And we'll come back to that. And then we said that these reagents, they work, going down below, by generating hydride, H-. And a mechanism for this, it's a little bit more complicated perhaps than it needs to be, is that this is borohydride here on the left, is introducing H-, which is going to nucleophilically attack the carbonyl carbon. And this is going to get coordinated to the boron, so it gives us this intermediate, which then it picks up a proton off of water to give us the alcohol. The same thing happens with lithium aluminum hydride, which looks like this. Lithium is the counterion. Same sort of mechanism. This is going to generate a hydride. This is going to coordinate to the aluminum. So we have this species here, negative charge on the aluminum, and then we're going to protonate to give us the alcohol. Alcohol will show the hydrogen that's there, and we'll end up with this. So those are the two common reducing agents. And a couple more things about these. One is a practical issue, is that because the borohydride is not nearly as strong as the lithium aluminum hydride, we'll see differences in the reaction conditions. Actually, I didn't say nearly enough room, so we'll try to squeeze some things in here. How about... This is a terrible thing, but if I can, I'm going to scroll all the way down here to the bottom. And if you want to continue in your notes, please, we'll put it down here for right now. So this is reduction, continued. Oh, can I add a page? Good idea, Christina. So, oh, there's one there somehow. Excellent. We'll do it here. So this is reduction. That reminds me, if you looked at, I uploaded just a very brief outline for Chapter 19, and there's about 5 or 6 pages at the end that are blank. I should have just added them. I did that so that we have extra pages at the end. Oh, I can also add pages in between. Excellent. So anyways, for the Chapter 19, then I put all those blank pages in there, but then later on I realized it might look like there's supposed to be something there, but there's not. On the top right, next to that, can I move? Oh, how about that? Oh, excellent. Okay. Oh, now I'm confused as to what's going on. I'll go back down to this one for right now. I'll figure this out for Monday. We want this one. So this is really disorganized now, but okay. So I'll organize this before uploading it. And then if anyone asks you later today, oh, how was organic chemistry this morning? So, oh, we watched him try to figure out notability for about 15 minutes, and so that's pretty exciting. We'll try this again. Reduction. continued. Okay, thank you for all of that. So I'll organize these pages. You're much more sophisticated on this than I am. I actually still really even haven't looked at what I can do on the iPad. I thought I needed to play games, but so far I've just used it for this class. All right, what were we talking about? How about all these borohydride reagents and lithium aluminum hydride? So one thing you'll notice is that if you have a ketone, and if you look at the conditions, sodium borohydride, this reaction can be run in the presence of water or alcohol, or something like ethanol is a common solvent as well. And you'll actually form the reduced product. However, you do not want to do this with lithium aluminum hydride because lithium aluminum hydride is much more reactive. And if this comes into contact with water, it will react vigorously, meaning it can start a fire. And so what you'll do is you'll use lithium aluminum hydride in an anhydrous solvent, like anhydrous ether, keeping water out, do the reduction reaction, and then at the end, when most of the lithium aluminum hydride has been used up, then you'll very carefully add in water. Just add it dropwise. So what you'll see is lithium aluminum hydride, it'll be done in 2 steps. And so this is saying you add LaLH4, let the reaction happen carefully. You're excluding all the water that you can, so you dry all your glassware. You keep everything under nitrogen or argon to keep the moisture out. Let the reaction happen. Most of this gets consumed, and then you very carefully add in water. So that's a practical issue of them. Then, I don't think we mentioned this yesterday, why is there a difference in reactivity? So when we look at, why different? Borohydride and the aluminum hydride, this one typically is the sodium salt, this one is the lithium salt. Just like when we were dealing with the organometallics, we saw that there was a difference in the dipole, or based on the differences in electronegativity, and that made the lithium compound, the organolithium, more reactive than the Grignard reagent, which was more reactive than the copper, the Gilman reagent. Same idea here, is that there's a greater electronegativity difference between aluminum and hydrogen here compared to the boron and the hydrogen. What this does is it makes this species much more like the hydride, H-. That's what we really want. That's what it's supplying. And the more it's like a true H-, the more reactive it's going to be. So that's the reason why lithium aluminum hydride, the one on the right here, is more reactive than the sodium borohydride. The last part with these reducing agents is, why do we really need strong versus weak? Why? How about we'll just say cover? Why cover strong versus weak? And this is one of those cases. Now, just like with the oxidizing agents, we had a choice sometimes with the primary alcohol. Do we use PCC or do we use the Jones reagent? We're going to see a similar situation here with these reducing agents. And so there's going to be more choices that we have to make. If we have a compound that has just a ketone, like what we've been using, a ketone or an aldehyde, it doesn't really matter which reagent we're going to use. We could use either one, lithium aluminum hydride or the sodium borohydride. However, that does make a difference if you have other functional groups. So I'm going to turn this into an aldehyde. So if we have an aldehyde or a ketone, we can imagine reducing those to an alcohol. Functional groups we haven't really dealt with yet, but we could have an ester, a common one, or even a carboxylic acid here. And those could also be reduced, and we'll cover the mechanism for those a little bit later. However, what you'll notice is that lithium aluminum hydride reduces all of these compounds. However, the weaker sodium borohydride will only reduce aldehydes and ketones. So if you have an aldehyde or a ketone that you want to reduce, it doesn't matter which compound you're going to use. However, if you wanted to reduce an ester or a carboxylic acid, let me go back to the different color. So our ester or our carboxylic acid, we've seen these already quite a bit. Ketone, aldehyde. If you want to reduce an ester or carboxylic acid, then we cannot use sodium borohydride, and we'll have to use the lithium aluminum hydride. As an example, imagine we had a compound that has a ketone and an ester that looks like this. If we were to then treat this compound with sodium borohydride in water, let's say we have an excess of sodium borohydride, we'll end up with an alcohol here, and it would be chiral, but we're going to ignore the stereochemistry now, and a primary alcohol. And we haven't gone through the mechanism of the reduction of an ester. We'll do that soon. However, if we use lithium aluminum hydride, and in the second step, water, I should put ether here. Oh, I'm sorry, I made a mistake. Right. I have them mixed up. This is going to stay as the ester. This is going to reduce this all the way to the primary alcohol. So since I kind of messed this up, let's start over again. We take this compound that has a ketone and an ester. If we treat this with the weaker reducing agent, the sodium borohydride, we're going to reduce the ketone, but we're not going to do anything to the ester, so that stays intact. However, if we end up using a stronger reducing agent, the lithium aluminum hydride here, now we're going to end up again reducing the ketone, so that's the same for both. However, we also now reduce our ester down to a primary alcohol. So in response to Hannah's question here, what we want to do is make something that allows this H minus to act more like the hydride. And as we're going down the periodic table, we're going from boron here in this period down to aluminum, and that's going to create the difference in the electronegativity, which should affect, here it's not serving as H minus so much, but I'm sorry, H plus, but we want it to serve as H minus, as the hydride in this particular case. And it is also more complicated. It has to deal with the metals as well. And so we're kind of simplifying here and just making this assertion that one is much more reactive than the other. Okay. All right, excellent. Any other questions about those two reducing agents? So you can see that now we have all these choices that are coming in. We have these different oxidizing agents like PCC and the Jones reagents, and now we have these different reducing reagents, the borohydride and the lithium aluminum hydride. Now I have to find where we were with our pages.